Hey class, Adam Ward here. First of 4 videos for you today about turbulent flow in pipes. You'll remember our previous topic was laminar flow in pipes. And so what we're going to do today is ask what happens when that Reynolds number gets up above 4,000, when we go from smooth, orderly flow with very little mixing to a turbulent flow where we get mixing across the streamlines and additional energy loss associated with that. Learning objectives for today, excuse me, you should understand what the Darcy-Weisbach equation is, and you should see how the Darcy-Weisbach equation can be used to get head loss or estimate head loss in the energy equation problem. We'll be able to use the Moody diagram and solve all 3 types of Moody diagram problems. All right, so if we were setting up a dimensional analysis problem, it might look something like this, where the pressure drop, delta P, is defined as a function of several other variables. Those might include the roughness of the pipe, epsilon, the geometry of the pipe itself, so its diameter d and its length L, the kinematics of the problem, how fast is the flow moving. Of course, what the fluid is may matter here. If it's air versus water or oil, you might get different energy losses. And that term on the left-hand side, what we're actually after. And we're assuming here that energy loss is going to take the form of a pressure drop. So this is a good opportunity, if you still need practice on dimensional analysis, to start with the problem that I've defined above. You would pick the anchoring variables of viscosity, length, and roughness. And you should be able to recover from that non-dimensional equation that looks something like this, where we've got the pressure drop equal to some function of the Reynolds number, the aspect ratio of the pipe, or its length to diameter, and epsilon over diameter. So how big is an individual roughness element relative to the diameter of the pipe? You might think about that as like the average fraction of the diameter where each little roughness would stick up. So this is what we know about turbulent pipe flow, right? We can relate these things, although we don't have an explicit mechanistic way to do so, but we expect that this is what would describe the relationship. What the Darcy-Weisbach equation does is formalize this a little bit for us. And I'm rewriting here what we had on the previous slide with one important change. You'll notice that I've taken this pipe length over diameter and I've pulled it out of that unknown. And the reason I took it out of the unknown function is what this is telling you is that energy is going to scale directly with length. You double the length of pipe, you expect to double the amount of energy loss due to turbulent flow and friction, right? So it's a direct scaling relationship. So what we're going to do then is take what I've boxed in red here, and although we don't know that relationship, we do know what it should depend on, Reynolds number and the relative roughness of the pipe. And what the Darcy-Weisbach equation does is it collapses all of that into some magical empirical factor called the friction factor, F. So the second thing that we'll do here is we'll write the energy equation for a horizontal pipe, so Z1 equals Z2, and for a pipe of uniform diameter. So if the diameter is the same at points 1 and 2, the velocity must also be the same at points 1 and 2. And so what you can recover from the energy equation then is this fairly simple relationship that says, hey, the pressure drop over specific weight, that is the head loss. In other words, all the energy losses that we have for a uniform horizontal pipe take the form of a pressure drop. And that should be comfortable for you. We talked about that in our laminar flow derivation as well. Now you'll notice both equation 1 from dimensional analysis and equation 2 from the energy equation both have that delta P in them. And so what we can do is we can combine those two equations and describe head loss as equivalent to the friction factor F times the length over diameter of pipe times V squared over 2G. So that is what's called the Darcy-Weisbach equation, and that is how we get these turbulent losses for pipe flow into the energy equation. So what you've just done in this couple of slides is you've taken the energy equation that we've been comfortable with, but we've not really been describing head loss mechanistically, and you've taken this idea of dimensional analysis and we've slammed those two together. So where we would have had some generic head loss term, we now can put in the Darcy-Weisbach equation. So the only problem at this moment is, well, what the heck do we do about this friction factor, right? In the bottom equation, it's sitting there, and up top in the red box, what we've noted is it exists and we don't know what it is, but we know it matters. Excuse me. So you've got a couple of solutions here. One is to go to an empirical set of findings, and this is what's called the Moody diagram. So let's introduce you to the Moody diagram. The values on the left-hand vertical axis, where I've just written that purple F, those are the friction factor that you should use. Along the x-axis, you see that's labeled as the Reynolds number, and I'll just note for you that that's a log scale, so you want to be careful when you're reading it. And then over on the right-hand side, you can see I've written in orange, that's the relative roughness, that epsilon over D. And so the way that the Moody diagram works is perhaps less than straightforward. Well, first off, if you've got laminar flow, you can see I've used this green to circle the word laminar flow, and I'm pointing you at this linear relationship. So for laminar flow, this friction factor is well estimated by 64 divided by the Reynolds number. And interestingly enough, for laminar flow, the roughness of the pipe doesn't matter. That's perhaps unsurprising if we think about it, because that friction or the energy loss in laminar flow is mostly about fluid scooching past other fluid. So yes, it has to do with the Reynolds number, but very little of it has to do with friction from the edges of the pipe. So if we're in the laminar range, we could estimate the friction factor as 64 over Reynolds number, and you can go ahead and use the Darcy-Weisbach equation. But what about over in the turbulent space? So as I've highlighted in purple, each of these black lines that you see represents a particular value for E over D. So if we take the value 0.004 that I've circled in purple, that line that I've highlighted or drawn over in purple, that line is the appropriate line to read to for that friction factor. Then what you would do is you find your Reynolds number, 2 times 10 to the 5th, for example. You read up, as I'm indicating with the red arrow, until you hit that E over D line, and then you read to the left to find the friction factor that's associated with that. So what we've just done here is to say, if you have a relative roughness of 0.04, and you have a Reynolds number of 2 times 10 to the 5th, you should use a friction factor of about 0.027. And so this Moody diagram is assembled entirely from empirical results, but it tends to work out well. The last thing I'll note for you here is that you'll see as these lines for a friction factor, so let me trace a lower one, a smoother pipe. As these lines get to lower and lower Reynolds numbers, they all start to collapse onto the same line. So I've traced one in yellow. If we trace another one in pink, they basically all start to collapse, and that's okay. If you find yourself in that collapsed region, you simply read up, pick your Reynolds number, read up to the collapse, and then read to the horizontal. Now, if that seems a little confusing to you, don't worry. There are a series of 3 videos to solve this, to solve problems using the Moody diagram to help get you comfortable with it. Now, that Moody diagram seems perhaps a little frustrating. Aren't there better ways to do this? So there absolutely are alternatives. I'm not convinced they're better, but they do exist. And what these are basically folks who are trying to take the empirical results on the Moody diagram and approximate them with relationships. And so one popular version of this is called the Colebrook-White equation, and that's written here for you. Now the challenge here is that this is implicit in friction factor. In other words, that friction factor appears on both the left-hand side and the right-hand side of the equation, and you can't separate them. So you have to guess a value for the friction factor on one side of the equation, see if it works or is correct on the other side of the equation, and basically iterate through that guess and check process until you converge on a value for friction factor. But again, you do see those same input dimensionless terms, Reynolds number and relative roughness. As an alternative to the Colebrook-White equation, there's one called the Holland equation. This is relatively easy to solve, so if you have your Reynolds number and your roughness, you can get a good estimate for your friction factor. The reason you might not use it is this is a best fit to the Moody diagram, and it's still not pleasant to type this into a calculator. Sometimes it's easier to just grab a copy of the Moody diagram and do these problems by hand. In all the examples I do for you, I will do them using the Moody diagram. So that's your option 2, use the Moody diagram. And I've split the Moody diagram into 3 types of problems. This is my own typology, so this is not something that if you Google Moody diagram type 2 problem, that's not something you'll find, but it's a good way for us to organize our thinking. So if we have what I call a type 1 problem, where the thing that you want to know is head loss, or that HL, if that's the unknown, you are quite happy because it's a straightforward problem. You calculate your E over D, you calculate your Reynolds number, you can read F from the Moody diagram, and then you've got your L over D, your Darcy-Weisbach equation that you can use. What I just wrote is equal to head loss. So a type 1 problem is straightforward. That's one that we're happy to see. Type 2 or type 3 problems, these vary depending on what you don't know. So if you don't know something about the flow, either velocity or discharge, or if you don't know the pipe geometry, meaning the diameter, or perhaps something about the length, you're going to find yourself in the same workflow. And this is a guess and check workflow. So in order to solve these problems, you'll have to guess a value for friction factor. If you have that friction factor, then you can go through and calculate the diameters, the lengths, the discharges, the E over D, or epsilon over D's, all of those values. You take what you've calculated from your guess to the Moody diagram, and you read a new friction factor. And you ask yourself, does the friction factor I read equal the friction factor that I guessed? Unless you're incredibly lucky, the answer is no the first time that you do it. So you take that friction factor that you just read, go back through all the steps, and you keep iterating through these calculations until the friction factor you guess is equal to the friction factor that you read. Okay, so this type 1 problems are explicit solutions. Types 2 or 3 are implicit solutions or iterative solutions. And where we go from here, 3 recordings of me solving problems, 1 of each problem type. And by the time you get through those, you should be an expert at using the Moody diagram, and these problems should be no issue for you. Thanks for sticking with me, folks, and I'll see you in the next video up.